One day, the last star in the universe will die. There will be no sunrise, no blue planets, no glowing galaxies in the sky, no warmth moving through space. Only darkness, stretching farther than any human mind can imagine. Today, the universe is about 13.8 billion years old, but this is only the beginning of its story. The future of the universe is not measured in millions of years, not even billions. It is measured in trillions, duodecillions, and numbers so large they stop feeling real. But the question is simple. If the universe dies, what happens after? Before we talk about the death of the universe, we need to understand what is alive today. The observable universe is about 94 billion light years across. That does not mean the universe is only 94 billion light years wide. It means this is the part of the universe whose light has had time to reach us. Beyond that, there may be much more, maybe infinitely more. In this visible cosmic ocean, ordinary matter is only a tiny fraction of everything. The atoms that make stars, planets, oceans, mountains, and human bodies make up only about 5% of the universe. About 27% is dark matter. It does not shine, it does not reflect light, but its gravity helps hold galaxies together. And about 68% is dark energy, the mysterious force linked to the accelerated expansion of space itself. So the universe is not mostly stars, it is mostly mystery. The universe is expanding, and it is not expanding like an explosion moving through empty space. Space itself is stretching. The distance between faraway galaxies is increasing. This is why many galaxies seem to be moving away from us. But here is the important part. The universe does not need to expand into something. When scientists say space is expanding, they mean the distances inside the universe are increasing. The balloon example is useful, but it is not perfect. A balloon expands into the air around it. The universe may not have an outside like that. It may simply be that space itself is changing, and this expansion is not slowing down, it is accelerating. About 9 billion years after the Big Bang, the expansion began speeding up. That acceleration is one of the biggest clues to the universe's future, because if expansion continues forever, the universe may not end in fire, it may end in separation. There is one question many people ask. If space is expanding, how can galaxies collide? The answer is gravity. Expansion dominates on the largest scales, between galaxy clusters separated by enormous cosmic distances, but nearby objects can still be held together by gravity. The Earth does not expand away from the Sun. The solar system does not get stretched apart by cosmic expansion. The Milky Way does not instantly fly apart, and our galaxy is still moving toward Andromeda. In about 4 to 5 billion years, the Milky Way and Andromeda are expected to merge into one larger galaxy, so both things can be true. The universe as a whole is expanding, but local gravity can still win in smaller regions. For now. The real danger comes if dark energy changes, if it becomes stronger with time. Gravity may eventually lose everywhere, even inside galaxies, even inside solar systems, even inside atoms. That future is called the Big Rip. The Big Rip is one of the most terrifying possible endings. It depends on one condition. Dark energy must grow stronger over time. If that happens, expansion will not only separate galaxy clusters, it will begin tearing apart smaller and smaller structures. First, the most distant galaxies disappear beyond our cosmic horizon. Their light will never reach us again. Future civilizations would look into the sky and see fewer galaxies than we see today. Then, over unimaginable time, the night sky becomes emptier. Galaxy clusters drift beyond contact, then galaxies themselves become vulnerable. If dark energy becomes powerful enough, even the Milky Way could be pulled apart. Stars would no longer remain gravitationally bound. The Sun would be isolated. The planets would lose their stable future. Then the expansion reaches solar systems. Earth would no longer orbit the Sun. The Sun would vanish from our sky, not because it died, but because space itself had stretched the relationship apart. After that, the Big Rip becomes even stranger. Planets tear apart, then rocks, then molecules, then atoms. Eventually, even the particles inside matter could be separated. There would be no planets, no stars, no atoms, no structure, no future chemistry, no observers, no clocks. Only space stretching everything beyond connection. But the Big Rip is not guaranteed. It requires dark energy to behave in a very specific way. Right now, scientists do not know enough about dark energy to say this will happen. It is possible, but it is not the most accepted ending. There are other futures, and one of them is the opposite of the Big Rip. Instead of everything being torn apart, everything falls back together. Imagine the expansion of the universe slowing down, then stopping, then reversing. Galaxies that once moved away from each other begin moving closer. The universe starts to contract. This possible ending is called the Big Crunch. In this scenario, the universe does not freeze into darkness. It collapses into heat. At first, nothing seems dramatic. Galaxies still shine, stars still form, planets still orbit, but slowly the cosmic scale changes. Galaxy clusters move closer. Then galaxies merge. The background temperature of space begins to rise. Today, the cosmic microwave background is only about 2.7 Kelvin above absolute zero, cold, almost silent. But in a collapsing universe, that background radiation would heat up again. Eventually, space becomes too hot for liquid water. That means biology as we know it becomes impossible. Then the universe grows denser, hotter, more violent. Stars are packed closer, galaxies lose their separate identities, planets melt, atoms are stripped apart, matter becomes plasma, the entire universe becomes a furnace. Finally, everything collapses toward a state similar to the beginning, a singularity, a point where our current physics breaks down. The Big Crunch is dramatic, but current observations suggest expansion is accelerating, not slowing. So under today's evidence, the Big Crunch is not the leading scenario, unless dark energy changes in the future. And that is the problem. We do not know what dark energy really is, if it changes direction, if it weakens, if it becomes attractive instead of repulsive, then the future could be very different. And if the universe collapses, one strange question appears. Could the end become another beginning? The Big Bounce is one of the most hopeful ideas in cosmology. It suggests that the Big Bang may not have been the first beginning. Maybe the universe expands and contracts, then reaches an extreme state, and expands again, not once, but over and over, a cosmic cycle. In this view, the universe does not die forever. It breathes, expansion, collapse, rebirth, expansion again. If this is true, then our Big Bang may have been only one chapter in a much older story. Before our universe, there may have been another universe, and before that, another. But there's a catch. We do not know if information could survive from one cycle to another. If a previous universe existed, its galaxies may be gone, its planets gone, its life gone, its history erased. A new Big Bang may not remember the old universe, and the laws of physics might be the same, or they might be different. Maybe gravity changes, maybe particles form differently, maybe stars are impossible, maybe life never appears. The Big Bounce is powerful because it gives the universe a chance at rebirth. But it is still speculative. It is not proven, and right now, the future that many scientists consider most likely is not a rip, not a crunch, and not a bounce. It is something quieter, slower, colder. A death so slow that it makes even stars seem temporary. It is called heat death. Heat death does not mean the universe becomes hot. It means useful energy runs out. Today, the universe has structure. Hot stars shine into cold space, energy flows, planets receive warmth, chemistry happens, life can exist, but over time, energy spreads out, differences fade, stars burn their fuel, galaxies grow darker, black holes swallow matter, the universe becomes more uniform, more empty, more silent. This is connected to entropy. Entropy is often described as disorder, but in cosmic terms, it is also about energy becoming less useful. A hot cup of tea cools down because its heat spreads into the room. The tea does not suddenly heat itself back up. In the same way, stars radiate energy into space. That energy spreads outward, and once it spreads too thin, it cannot do work anymore. Heat death is not one explosion. It is the slow loss of possibility. The universe does not scream, it fades. Right now, we live in the stelliferous era, the age of stars. This is the bright age of the universe. Gas clouds collapse, stars are born, planets form, supernovae spread heavy elements, black holes grow, galaxies evolve. This age began when the first stars ignited a few 100 million years after the Big Bang, and it will not last forever. Star formation depends on gas, mostly hydrogen, but every generation of stars uses some of that gas. Some is locked into stellar remnants, some is blown away, some falls into black holes. Eventually, galaxies will run low on fresh star-forming fuel. The last normal stars are expected to form somewhere between 1 trillion and 100 trillion years from now. That is up to about 7,000 times longer than the current age of the universe. Our sun will not last that long. In roughly 6 billion years, it will approach its red giant phase. Earth's oceans will be gone long before the far future of the universe begins. The sun will shed its outer layers, then it will become a white dwarf, a hot stellar corpse, slowly cooling in space. But even after the sun is dead, the universe will still have stars, mostly small red dwarfs. These stars burn fuel slowly. Some may shine for trillions of years. They are the final candles of the stelliferous era. But even the longest burning stars eventually run out. And when the last red dwarf fades, the universe enters its next age, the age of stellar corpses. After the last stars die, there will be no new sunlight, no ordinary stars, no warm golden suns, only remnants, white dwarfs, brown dwarfs, neutron stars, black holes, cold planets drifting in darkness. This is called the degenerate era. It could last from around 100 trillion years into the future to unimaginably later times. White dwarfs will cool, they will no longer shine white. They will become black dwarfs, objects so cold and dark that they emit almost no light. The universe at this stage would be almost impossible to recognize. Galaxies would no longer glow with billions of stars. They would become graveyards, dark remnants orbiting each other in silence. Occasionally, two dead objects might collide. A black dwarf might meet another black dwarf. A neutron star might fall into a black hole. A rare flash might appear in a universe that has forgotten light. But these events would be separated by enormous stretches of time, longer than the entire current age of the universe, not once, but trillions of times longer. If protons decay, matter itself may slowly fall apart. A proton is one of the basic building blocks of atoms, but proton decay has never been observed, so this part remains uncertain. If protons do decay, then planets, dead stars, and ordinary matter will eventually dissolve into lighter particles. If protons do not decay, some dead objects may survive much longer, but even then, gravity and black holes still wait. In the far future, black holes may become the last major objects in the universe. They are the final survivors of gravity. A black hole can outlive stars, outlive galaxies, outlive planets, outlive almost everything made of ordinary matter. But even black holes may not be eternal. According to Stephen Hawking's theory, black holes can slowly lose energy through Hawking radiation. For small black holes, this process is faster. For huge black holes, it is almost unbelievably slow. A black hole with the mass of the Sun could take around 10 to the power of 67 years to evaporate. That is a 1 followed by 67 zeros. Supermassive black holes could last far longer. Some estimates place their evaporation times near 10 to the power of 100 years or more. The Google years, a 1 followed by 100 zeros. By then the word ancient has no meaning. The universe will be older than every star that ever existed. Older than every galaxy, older than every planet, older than every possible civilization. Then even the black holes fade. One by one, the final black holes release their last radiation, a last whisper of energy in a universe almost completely empty. And after that, there is no known structure left. After the black holes are gone, the universe enters the dark era. There are no stars, no galaxies as we know them, no planets with sunlight, no black holes, only scattered particles, photons, electrons, positrons, neutrinos, maybe dark matter particles, if they survive. The universe continues expanding, but almost nothing happens. A particle may travel for unimaginable distances without touching anything. An electron and a positron may occasionally meet and annihilate, but such events become incredibly rare. Time still exists, but change almost disappears. There is no day, no night, no seasons, no sky, no chemistry, no life as we understand it. The universe does not become nothing, it becomes almost empty. And that difference matters because empty is not the same as nothing. There may still be space, there may still be particles, there may still be quantum fields, but there is no usable energy left to build stars, worlds, or life. This is heat death. Not an explosion, not a collapse, not a final scream. A silence that keeps going. So what happens after the universe dies? The honest answer is, we do not know. If the Big Rip happens, the concept of after may break down. If space, time, and matter are torn apart, there may be no clock left to measure what comes next. If the Big Crunch happens, the universe may collapse into a singularity. Maybe that is the end, or maybe it becomes another Big Bang. If the Big Bounce is true, death may be part of a cycle. A universe ends, another begins. But if heat death is the true future, then the universe may continue existing forever. Almost empty, almost frozen, almost changeless. It may not end in the way humans imagine endings. It may not close like a book. It may simply become unreadable, still there, but silent. The strangest part is this: the universe may have no purpose that science can measure, no promise that life will return, no guarantee that another Big Bang will follow. But somehow, in this temporary bright era, stars formed, planets cooled, atoms joined, carbon chemistry became alive, and on one small world, creatures appeared who could look up, measure the age of the cosmos, detect dark energy, calculate black hole evaporation, and ask what happens after everything ends. That may be the most incredible fact of all. Not that the universe will die, but that for a brief moment, it became aware of itself, through us. One day the last star will fade. One day the final black hole may evaporate. One day the universe may become a cold ocean of particles, too far apart to remember each other. But today, the stars are still burning, galaxies still shine, planets still turn. And somewhere in the darkness, we are asking questions that reach beyond time itself. Maybe the universe ends in silence. Maybe it begins again. Maybe nothing comes after. Or maybe the word after belongs only to creatures like us, living in the brief age of light. This was Ejecta Earth, where ancient worlds die and the universe reveals its final secrets.